Thanks, Juho. And thank you, Wunderdog, for having all of us here. And thank you to all of you too for joining us on this Tuesday. Let's maybe start with taking a bit of a temperature in the room about various topics. How many people here have done front-end development? That's more or less everyone, okay. How about audio programming? A good few of people as well. Music production, new language synthesizers, that kind of stuff. Cool. How about WebAssembly? Nice. And how about C programming? Okay. It's a good mix of people. All of these topics are kind of swimming around this kind of weird soup that I'm going to be cooking here. Because I'm going to talk about making audio, making music in a web browser out of basically nothing except some C code. And there are various reasons I want to talk about that. One is just that professionally, this is something I kind of have to do sometimes. Kind of history of audio programming is such that much of the code that exists out there is C and C++ for various reasons. So when you want to take like a serious audio system and put it on a web browser, you usually have a pile of C and C++ code with you, and you need to kind of get it running in the browser, and WebAssembly is the tool for that. It was a bit intimidating to me at first, but when I discovered how little there is to it, I found it kind of quite exciting actually, and that's why I'm going to talk about that today, basically. So what we're going to do is take some C code, compile it to WASM, run it in a web page. Hopefully that'll turn out all right. So when you talk about audio in the web browser, everything starts with this object here. It's called the audio context. It's the entry point to the so-called web audio API that has existed for 15, 20 years now, at least 15 years now. Comes in every web browser, provides you with an API with which you can connect to the sound card on the computer that's running the web page and do audio processing and audio synthesis. One of the things you can do with web audio contexts these days is to make these things called audio worklets, which are kind of a newer addition to the web audio API, although even those have been around for several years now, maybe at least 5 years in all the browsers. And these things allow you to essentially write your own digital signal processing code to define on a very low level, audio sample by sample, how you want the audio to be processed. So it lets you inject JavaScript, or as we'll see, other languages in the audio thread that the browser is running and do whatever you want to do there. So once you construct one of those, what you load up onto the audio thread is one of these things, an audio worklet processor. So this is a class that you extend in which you do your audio processing. So this is the sort of thing that where all the magic happens on the audio thread. It has this one method that is central to it called process, which is a method the API will call for you every time it needs some audio to be synthesized. And that'll be called for 48,000 samples, or in other words, 48,000 floating point numbers per second, 128 of them at a time. So it gets called basically 375 times every second without fault. And every time it's called, your job is to put some audio into those outputs and get as an argument. And then that will fly straight into the whatever sound card you have connected. Now, if say you have some C or C++ code, as some of you on the show of hands have had the privilege of using before, lying around, in which you're doing whatever, audio processing. This is quite typical, as I said. There's various reasons why C and C++ are so popular with audio, to do with mostly performance reasons, one of which is that because this is real-time code, because you need to produce this audio signal 48,000 numbers per second very consistently, because if you're late with that, there will be an audio glitch which no one wants to hear. You can't have things like garbage collection and things like that kind of happening on the audio thread at like weird times when there's no time for it. You kind of want to have a language that has memory management that is very deterministic. And also just C being very low level in that you're literally just accessing the virtual memory, huge like array of memory block. There's no abstractions of like lists and collections and things like that that kind of get in the way of you being able to reason about what exactly how many CPU instructions is going to happen in various places. And that's why C and C++ are there, although these days I think a big part of the reason is just kind of entrenchment in that when there is 40 years worth of code, audio code out there, it's not going to go away anytime soon. But it's also kind of fun to add to that pile of legacy C code by making some new programs. And so here's one example. Short snippet of a C program that has a few things in it. There is memory block, floating point array, basically, of 128 floats. And that'll be the memory area into which we can write audio in this program. And then there's a function, in this case called make some techno, whose job is to make some techno and then return a pointer to it. And what you do in there is you loop over the array and do your audio processing. So you know you're always going to have in web audio 128 samples to process. That's what you loop over and put something into that array. In this case, I'm just putting in zeros to begin with, so we can have something to initialize the array with. We will be putting more interesting numbers in there very soon. Once you're done with that, you return it or return a pointer to it. It's the memory address of that array in the memory of the C program. And then the caller can use that to access that memory. So if that's your C program, you can turn it into WebAssembly by compiling it. Emscripten is like a popular tool set for doing that with. How many people are familiar with Emscripten? To some extent. A handful of people, yeah. So it's basically like a compiler linker tool set that takes languages such as C and C++ and things like that. Anything that I think produces LLVM bytecode and turns that into WebAssembly. I should say, though, that you don't actually need Emscripten to do this kind of thing. You can just use Clang, as I've done a few times, which is the LLVM C compiler, can emit WebAssembly directly without using Emscripten, but Emscripten adds a lot of kind of nice abstractions on top that makes it a bit easier. Anyway, what you do with that is you take a C file, techno.c, say, please turn it into WebAssembly in this file, techno.wasm, and please make these functions that are in the C code available as the public API of that module. And it pops out a WASM file. Once you have that, you can go back to your web page where you have initialized your audio context, loaded your worklet, and load the WASM buffer, or the WASM file that was outputted by the compiler. Just fetch it from your server, take the array buffer binary representation of that, and then you can send it over to your audio worklet. Audio worklets have this message port API, which is the same API as things like web workers have also, which is basically this async message-based communication between different execution contexts in the browser. So we are here on the main thread of the page. We have something, in this case a WASM code buffer. We post it over to the audio thread, where we cannot do HTTP requests, but we can receive messages. So we send it over, and then on the other side, when we have our processor running on our audio thread, we receive it. So we use the message port of that worklet to attach the on-message handler, take the WASM code in it, and then we turn that into a running WebAssembly module. And this stuff I'm doing here is kind of the standard WebAssembly thing, which has nothing to do with audio worklet specifically. It's just what you always do. With WebAssembly, you instantiate a module by giving it the buffer into the code, the compiled code, and you get back a WASM instance, which has the exported API in the exports member. So this will have the functions that you have exported in your C code or whatever code you have. And then you have the memory that it's using internally. So literally the same memory as the C program in this case is using will be in there as a typed array. Once you have all that, you can start using this thing. So in your process method, which is now where the audio is actually being constructed, 48,000 numbers per second, every time this callback gets called, we can reach into the C code, say, make some techno, please. And it'll return that pointer to the float array that was in the C code, which will have 128 floats of techno. And then you copy that over to the audio worklet's output array. So this stuff is basically a mem copy. So we're taking an array buffer view, the floating point array, of the WASM memory at the memory address that it told us things will be found in. There's going to be 128 numbers there. So that kind of gives us a float window into the WASM memory. And then we copy it over to the first channel of the first output of this audio worklet, which is another float32 array. And we use the set method to make essentially what boils down to a mem copy between these two memory areas. I should say that this bit of the Web Audio API, I think, is going to go away at some point. You are going to be able to say to the Web Audio API, I want you to access this memory directly in, say, a WASM module. So you don't have to do this copying, but right now you kind of need to do it, but it's pretty fast, so I don't really mind. And that's the kind of the whole bridging thing. You have some C code, compile it to WASM, you load it, you send it to the audio worklet, you make a WebAssembly instance, and then you just call it and copy over whatever it produces. That's the whole kind of integration process. And with that out of the way, we can then start focusing on, okay, how do we actually make some music to put in those 128 floats at a time? Because right now they're just zeros, which doesn't sound very interesting. So let's talk about that. Let's start extending the C program here. First of all, let's do some basic bookkeeping. We know that the audio process in this audio context is going to have a sample rate of 48,000 floats per second. From that, we can calculate a constant of how long of a duration a single sample in that audio stream is going to be, which is 1 second divided by how many samples there are per second, 48,000, which amounts to about 0.02 milliseconds. That is how long of a time window a single float defines in that audio waveform that comes out. And this will be useful for us as we calculate various timing related things, because we know, based on that, various things about how long we've been generating audio for. Then we can define our first sort of building block utility function that kind of can be used to shape audio signals. We will be making a phaser, which is essentially like a little ramp that starts at 0 and grows gradually to 1, drops back to 0, grows up to 1 again, and does that forever, basically. And you can define that as a function that takes the current phase of whatever the state of that phaser is currently, and the frequency, which is how quickly you want it to grow up to 1. And the way that works is you take the current phase, and add to it however much that should grow for a single sample. So we know how long a sample is now, and we know, or we don't know, but we will know what the frequency of the phaser should be. So if we multiply those together, we know how much the phase should grow in the duration of a single sample. And then, as I said, this goes from 0 to 1 and then drops back to 0 again. So we need to make sure when that exceeds 1, we drop back to 0. We can do that by subtracting from it the kind of floor integer of it. So when it goes to 1.1, we subtract 1 to get 0.1. And that way we keep it wrapped in that domain. And that's our phaser. We just return it. Now, once we have one of those, we can use it. So we can introduce a state phaser called kick phase. And then whenever we're in this audio loop, which is where everything will happen, we can say, well, okay, let's say this phaser is currently at the frequency of 200 hertz, which is like 200 times per second doing its phasing thing. We just call it with the current phase and the frequency, and we will get this kick phase variable, which gives us that 0 to 1 ramp, now 200 times per second. Now, to turn that into something audible, we can generate a sine wave based on that. So what we do is we call the sine function from the C standard library with this phase. And if you remember some math or trig, the sine wave has a domain of not 0 to 1, but 0 to 2 pi, because it goes around a circle. And there are 2 pi radians in a circle. So we multiply the phase by 2 pi. And out comes a sine function value that goes around 200 times per second, or 200 hertz. And in other words, a sine wave. And that is going to be a maximally loud sine wave in this case, because the domain of, or the output domain of sine function is -1 to 1. And that also happens to be the maximum amplitude in web audio. So 1 to -1 is you can't have a waveform louder than that. And we don't want this to be a maximally loud sine wave. We want it to be more quiet than that. So we multiply the output by some number less than 1 to just shrink it down. So in this case, it would be -0.15 to 0.15. And then we put that into the output array. And that should give us a sine wave. And now is the moment of truth of whether I've connected everything correctly here. There we go. 200 hertz sine wave. This is the hello world of audio programming. In this case, done from like low level, like mathy C. We have a phaser that does this thing 200 times per second. And then we take the sine of that to get a sine wave that does this to 200 times per second. And that's what that sounds like. Now, that's not quite, as far as techno goes, that is the most minimal techno I can imagine. We can do better than that, I think, by starting to shape that sine wave, first of all, over time, so that it's not just always the same volume. And to do that, we're going to do a bit more bookkeeping here and start to count where we are in the timeline of this audio process. So if we, first of all, just count samples, like have a variable that counts the number of samples that we've generated since the beginning of this program in one 64 bits, I think, long variable there. It's going to grow from 48,000 in 1 second, and then 69,000, and then to millions, however long this runs for. And then if we multiply that in the loop by the duration of one sample, we will get the information in seconds where we are currently in this track or in this stream or whatever you want to call it. So now we know how many seconds we've been generating as a kind of fractional floating point number. This is then useful for doing stuff, such as starting to count on different time domains, say the number of beats that we have been generating. So a fairly standard sort of tempo in electronic music is 120 beats per minute. That's another way of saying 2 beats per second, which we get by simply multiplying the time in seconds by 2 to get the number in beats that we are currently, which gives us a way to kind of count time in more musical terms in like whatever tempo we want to be using. Then we can also count where inside a given beat we are at the moment. So if we take the float beats and subtract from it the trunk or the floor that we already used in the phaser, we know where inside a beat we are. So that'll be 0 at the beginning of a beat, grow to 1 over that beat, and drop to 0 again. So it's kind of a phaser again. Just it's completely synced totally with the beat. That's something we can use to generate something called an envelope. So an envelope is something that you use to kind of shape a signal by some function that is, say, a phaser or something that kind of varies over time. So in this case, I'm going to make a so-called decay envelope, which is a thing that starts at 1 and drops gradually to 0. And I can get that by simply subtracting from 1 the T here, which is one of these phasers, which kind of just inverts it. So instead of having something that goes from 0 to 1, here's something that goes from 1 to 0. And then we have this amp argument here as well, which lets us, by multiplying the 1 to 0 ramp with that, get something that goes from amp to 0, like an arbitrary size of envelope. And this will be useful as a building block for various things today. But it's kind of another rampy thing. It's not very different from the phaser that we made earlier. But now we can use that. We have our kick sine wave. If we multiply that by an envelope that is based on the position in beats, and say make the amplitude stay at 0.15, we get something that actually has time varying quality, like that. And that's a lot better than just a sine wave. We can go further. For example, we can make that an exponential envelope, which is to say shape that kind of linear curve from amp to 0 to make it sound a bit more interesting. If we say raise it to a power greater than 1, we get like a shape that goes like that instead of going linearly, which is another way of saying we're basically using an easing function. If you have done, say, animation timelines, this is an ease out, exponential ease out of a linear curve, which looks like that, which also sounds a bit different. So if we use an exponent of, say, 3, it'll already have that kind of thing where it grows quite a lot more quickly, and then that allows you to kind of shape the kind of sound that makes, which is cool. We can also use envelopes for things other than the amplitude, including the frequency. So we have a frequency of 200 hertz for this sine wave at the moment. It doesn't have to be constant 200 hertz, because we can pass that into an envelope as well. So say make an envelope that runs from 200 to 0 with an exponent of 3, and then we add like a constant 50 to it. We get a varying frequency for the sine wave over the beat that goes from 250 hertz to 250 hertz. That's that kind of thing. And then if we really push that further, make it a really dramatic envelope from 950 hertz to 50 hertz with a very large exponent of 50, it starts to sound like this, which gives us a kick drum. This is, I think, this kind of very fast sweeping sine wave from high frequency to low frequencies, essentially invented, I think, in the 70s or something with early drum machines. But it's still very useful. Kind of just from a pure sine wave, you get something that sounds very much like, or is really a kick drum or a bass drum, which gives us the foundation really for what we're going to be building today. Now, once we have a kick sorted, we can talk about other instrumentation. Say bass. So sub bass, which I can add here by just doing stuff we've already done earlier. Let's decide that it's going to be a frequency of 50 hertz, and then we run a phaser like that, as we already did with the kick. We get a sine wave out of that, and we use an amplitude of 0.2 to just choose a loudness for it. And then we mix it in with the kick by simply summing the outputs of those two numbers. That's basically linear mixing. You just get two audio signals and you plus them, add them together, and you get both. Which gives us a bass. We have a pretty good sound system here because we can actually hear a 50 hertz sine wave. Not like a laptop can't produce a sound that low. Usually laptop speakers can't. But we can actually hear it, which is nice. A very kind of low end thing there, which is still just a sine wave though. We can add some more, let's say, character to it by shaping it a little bit more. We can use a process called saturation, which is essentially wave shaping, which is essentially just taking a sine wave and messing with that a little bit by, in this case, passing it through an hyperbolic tangent function, which just takes like a pure sine wavy thing and just squashes it a little bit so that the ends of the sine wave are a little bit more flat, which has the effect of adding harmonics to that basic sine wave. You can see them in the spectrum there. You can see more peaks turning up there. You can also hear a bit more texture in the sine wave now, so it has a little bit more of a kind of gritty quality to it, which also on like a normal laptop speakers would make it audible, because it wouldn't have been audible before because it's too low. Now it has components that are in the audible range for even like shit speakers. And we can drive that more. We can just like saturate it more by multiplying the input of the tangent by some number larger than 1 to make it a louder sine wave, which makes the tan H function work harder to squish it more, which shapes it even more. Then you get more peaks in the spectrum, more partials in the harmonic series that it's producing. That's good stuff for a bass. There is a bit of a problem here though, which is that it's still just like a sine wave that's kind of not a sine wave anymore, but it's a wave that doesn't vary over time at all. It's just there forever. What we ideally want here is a bit of interplay between these two elements. We have two things in the low end. We have a kick and a bass. We ideally would want them to have a conversation of some kind, to kind of have some more rhythmic interest. We can do that, for example, by introducing some process called side chaining or side chain compression, as it's often called, by which I mean basically the basic idea that when the kick is loud, we want the bass to be quiet, and when the kick grows more quiet, we want the bass to grow more loud. They have take turns basically, and you often do that with like an actual compressor, which might be like an effect in your jaw or an actual like guitar pedal or whatever. But we can kind of emulate that with some basic math here, which is taking an envelope and taking the inverse of the envelope, which is to say, instead of having an envelope that starts high, goes low, it starts low and goes high. It's just doing the inverse as the kick envelope, as what the kick envelope does. So with that, you can kind of see how it dips when the kick comes in. So they take turns in a way. And by changing the exponent here, we can manipulate the timing of that, because the exponent, the easing of the curve, essentially controls how fast it'll grow quiet. And by messing with the numbers, you can find something that sort of works with whatever tempo you're operating with, to get that kind of pumping effect down in the bass. Right, pretty happy with the bass now. We can throw in one more instrument. We'll call it chords. And to begin with, I'm going to do, once again, exactly what I did earlier, which is choose a frequency. In this case, I'm going to multiply the bass frequency by 4, which is 2 octaves above the bass now, which is 200 hertz in this case. And then we run a phaser, we take a sine wave, we do an envelope, all the same stuff that we already did, and add it to the mix. So get another sine wave with an envelope. That envelope or that rhythm is not really that interesting at the moment though, so we can make that quicker. We can count time, not just in beats, but also 16th notes. And a beat is a quarter note, in other words, in music and basic music theory. And the 16th is 1/4 of that. So it's kind of just a 4 times faster timeline than the beats. So what we get that by multiplying the beat counter by 4 to get a number that's 4 times quicker than that. And then take the trunk again to get like a little number that goes from 0 to 1 inside the 16th note. If we use that as the basis of the envelope for the chords, we get a quicker rhythm for that. Then we can also start to kind of do some patterning here to say, maybe we don't want that thing to trigger on every 16th note forever. Maybe we just want to trigger on some of them. So we can start making little patterns, like numeric patterns from, say, zeros and ones. In this case, I'm making one that's 16 numbers long, that goes for 1 bar of 16th notes, and then just define that. 0 means we should not play a chord on this 16th note. 1 means we should play a chord on this 16th note. And by choosing a configuration of 1s and 0s, we get some sort of rhythmic pattern going. Because you can, inside the loop here, when you know your 16th counter, you take the modulo, that modulo 16 to get like an index to that array. You get whatever numbers in that index in that array, and then you multiply the envelope with that, which means when it's 1, it's going to stay, when it's 0, it's going to disappear for that beat. And obviously, various different patterns could be made by using different zeros and ones and generating different ones in code. And it's kind of fun to start playing with that. But I want to kind of switch focus now to the sound design of these chords. We're using yet another sine wave here. We could use something else, another waveform basically, to make it sound a bit different. Say, for example, a sawtooth, which is a waveform that looks like that, like a sawtooth. And I'm using a function here called saw6, which doesn't exist in C standard library, so we should make one. This one is going to be a so-called additive sawtooth wave, which is a way of saying we're going to build this sawtooth out of sine waves, because we already have sine waves and we can do stuff with those. So for those of you who are a bit more into audio, we could like do a sawtooth just by counting like a phaser in reverse, because that also looks like a sawtooth. That has a bit of an issue though, because it has very sharp angles, and when you use that as an oscillator, you get this problem called aliasing, where you have sharp angles like that come out as weird sort of distortions in the spectrum. That doesn't sound very good. And you would have to do like anti-aliasing, add some more code to get rid of those angles and kind of do a lot of stuff to make that nice. What I'm going to do now will let us ignore those problems by making this out of sine waves and kind of just choosing that we're only going to have 6 of them, which is not going to grow high enough in the frequency range to become a problem with aliasing. So that's one reason why I'm using sine waves here, but it's also kind of just a cool thing to be able to do. You take a sine wave, you add to it another sine wave that is twice as fast and half as loud, and it changes the sound. You can also see 2 peaks in the spectrum here. Those are the 2 sine waves. You can do that a third time, a sine wave that's 3 times as fast and a third in amplitude, and then stack those up to 6. And that's a sawtooth. If you kind of saw that as an oscilloscope, it would look like this basically, but a bit more round and less pointy, which doesn't have aliasing issues. And it's done from from just sine waves, because a sawtooth wave is defined as all the harmonics of the fundamental frequency that yields a sawtooth-looking thing. So we can just do that here. Now, I was calling this instrument the chords. And we have noticed there's no chords going on here. There's still just a single thing, single frequency, which is 200 hertz. That we can extend by just running more of these in parallel. So we can say, have two phasors, one of which is the 200 hertz, another is that frequency times 3/2, which is a perfect fifth, a just perfect fifth above 200 hertz. If we run saw with both of those, sum them together, we get a interval of perfect fifth. And then we do a third one to make it a full minor triad by doing another interval. 6/5 is a just minor fifth over 200 hertz in this case, and put that in. The minor triad is the only chord you need in techno, which is useful for us because that's all it is, usually, especially like minimal dubby techno like this. And that's our chord instrument. I might do one more thing with that though, because it's now playing the same chord forever and ever and ever. Very minimal. But we might have, say, two chords to make it three. And what I'm going to do there is start which bar we're playing. So we had beats, which is for this thing that we got by multiplying the seconds by 2. We got the 16ths, which is 4 times faster than that. And then now we have bars, which are 4 times slower than beats. So there's bars, there's 4 beats per bar, and there's 16 16ths per bar, or 4 16ths per beat. And that's the kind of metric hierarchy we have in this 4/4 time. Anyway, bars we were not counting before. We now can get that by just dividing the beats by 4 to get a counter for bars. And I'm going to only need the integer part of that, so I'm not going to even bother with floats. Just have the language floor it down for me for the nearest integer below, because all I need to do with that is just check which bar we are in, because what I want to do is say have a 4-bar pattern where the last 2 bars of every 4 bars have a different chord. So if I take the modulo of the bar modulo 4 and check if that's 2 or 3, that'll be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and the 2 and 3 is where I want to do stuff. In this case, take it a perfect fifth down, which is to divide it by the interval of perfect fifth, 3/2. In this case, multiply it by 2/3, which is the same thing. And that will have it vary. Now, I want to do just one more thing, which is to add an effect to these chords. Delay effect or delay echo thingy, which is very standard in, say, like dub techno, of the kind of thing I'm doing here, which is an effect that takes any audio signal and repeats it after some amount of time. And for that to happen, we'll need to add some memory where we can remember some window of audio we have been generating. And so I'm going to introduce a floating point array here that can hold up to 1 second of sound by making it the size of the sample rate, which is 48,000, 1 second. It's going to initialize it with all zeros. Then I'm going to define the process delay function that will do our delay effect. It takes an audio input sample and the time by which it should be delayed, and returns the delayed version of that input. And the way that works is you run an index where you are in the delay line, array index. And whenever this gets called, you write the current input into the array at the current index. Then you increment the index to go forward in the delay line or in the array. Then you ensure you don't exceed the delay time that's been given to you. So we are only using the first X numbers in that array, which is defined by the delay time. So if we go beyond that, we circle back into 0. So we have another kind of circular counter here. And then we return whatever is in that updated index. And this whole thing has the effect of numbers you put in there come back out after some delay time from that same array. This is called a circular buffer delay line, and it's very common in audio because you want to have this thing where you can write into the array in one end, read in the other end, but doing stuff like actual queue data structures, which have a lot of like operations needed to make that going. So this is like a single array, and all you do inside the tight audio loop is you increment this one index by which you read. That goes around the array, so you don't have to move memory around. You just kind of index it. It doesn't need many instructions, and it's fast to do. Especially when you have like reverbs and stuff that you build out of literally like 50 delay lines. It gets important how much math you need to do to run these. We have just one, so it's not really that much anyways, but it's still like a nice thing to do it efficiently. Anyway, delay. Plus delay is a function that we now have. We can take our chords, run them through the delay line, choose a delay time of 0.7375 seconds, which in this tempo is a dotted eighth note. And we add the delayed version to our original version, multiplied by a number, in this case 0.4, to make them more quiet. So the delayed version is more quiet than the original, which gets that repeating effect. So every chord hit is followed by another one soon after. And then we can make that into a feedback delay or an echo delay with a simple extension, which is another argument, feedback, to the function. And then this modification on the first line, which says, when we write the delay line, we don't overwrite what was there before. We just attenuate it by taking whatever was there and multiplying it by the feedback. So when say, a sound gets into the delay line, it kind of repeats many cycles through it, getting more quiet every time by this feedback, but it still kind of bounces around in there, which is very useful for echo type sounds. So if we say choose to have a feedback of 0.5, we get this kind of echo effect. And there we have about 100 lines of C code, which makes music like that. Using no libraries, no samples, no anything. A handful of functions on the C standard library. So sine, tanh, trunc. I think we're the only three. And the rest is just a bit of arithmetic, really, and some array indexing. Compiles down to not very much WASM code. UK, I think, in this case, probably. There are probably ways to make it smaller, even if you're into demo scene stuff, you might be very offended by how much code I'm using to do this, but it's still not much by my standards. And obviously, hopefully you can see how, since it's code-based, we could go to town doing interesting algorithmic patterns and variations, and sound design based on like pure logic in here. And it runs in the browser. Takes about maybe 1% of the CPU of my MacBook here. And it's doing that. Code is up on GitHub if you want to see it. or play with it. And with that, I thank you. And I suppose we have time to discuss or have QA and...
Yes, so if you have any questions, just grab the mic and hit Tero. So if we ignore the use case of having existing C or C++ audio processing code, are there scenarios where JavaScript just doesn't cut it into the audio code?
JavaScript, I would say, yes, there are. It's mostly due to like efficiency of the code. So, for example, you want to do numeric DSP stuff, a lot of like arithmetic, of essentially mostly lots of multiplication and additions. Often also SIMD, like parallel vector-based processing, which you just can't do in JavaScript. And in JavaScript, there's only the one numeric type, which is the float 64 double. You don't always want that. And you want to know exactly which CPU instructions your math compiles down to. So you want to have these data types around. And then the other part is GC. So you can write JavaScript that doesn't produce garbage, which means you won't ever have garbage collection issues, but it's like kind of hard to remember or kind of be, what's the word, like constrained enough or disciplined enough to write that specific subset of JavaScript that doesn't get you into trouble. And for that reason, you want to have more low-level languages, not necessarily C. I mean, plenty of people use Rust now as well, and other languages that have more systems programming characteristics. There are also like more niche languages like that are purely meant for audio. Like there's one called C major that is a good name for a language, I think. That's being done by the people who wrote the Juice audio framework. It's like a new C-based language that doesn't have the problems of C, but is still kind of low level, designed to be for this kind of numeric efficiency. But yeah, I mostly don't use JavaScript now because it has problems with too many cycles. Can you put the screen back on? Cool. Thank you.
Okay. I don't really have a question. I think this is one of the finished short question. I believe we just before. I wanted to ask you how did you create the presentation one like you said in previous, it looks really good with code handles. What do you use? Is it Slido or?
It is not Slido. It is called CodeSurfer. This one, which does all this stuff. It's based on this framework-ish thing called MDX-Deck, which is for React, which lets you define your slides in MDX, like Markdown, and then it adds this kind of code, highlighting and transition capabilities to it. It's, I think it's not maintained anymore, but it still works. So that's, yeah.
Right. Yeah, thank you for the talk. I was interested in what kind of build system are you using? What is your loop like when you're
Yeah, that's a good question. To be honest, I quite often just like run the compiler when I need to need a new version. I do though, because it's C and most of the kind of actual projects we work on, we don't deploy to the web primarily. So we quite often have like the audio engine that's primarily used, say, in iOS and Android apps. And so I have a native build process in Xcode, usually, or something like that. where I do all the actual changes and then like compile to web out of band, like out of the normal dev loop. But I'm not very good at having like automated feedback loops. I often berate myself for not being too lazy to set that up, but I just run the compiler 1 million times during the project. It's fast, so it doesn't really matter. Rust would have a different problem with that. But,
Yeah. Do you have any, like, have you learned all of this yourself, or do you have any resources you would point to someone who's interested in learning like this programmatic approach to making sound or music?
yes, I've sort of learned it myself from various like random sources online. What I often recommend to people who want to kind of get into it without all the like necessarily coding in C is MaxMSP, and especially Gen, which is like a subsystem of MaxMSP. It's a visual programming language where you get to do these. That's not what I was looking for. Which might help, by the way, but I don't know. Like these kinds of things, where you make like sample by sample audio processing, but visually, and you have that instant feedback loop of like you hear exactly what change you make in real time, and there's really good help systems and like example patches in there. So that's how I learned a lot of like basic DSP stuff, because it's essentially math, but reading about it is very boring, because you want to hear it. So this is kind of the environment you want to get into for that kind of stuff. And then for like there's lots of good books on like writing. If you want to get into say audio plugin development for like making actual plugins for producers in C++ and frameworks based on that, which I've also kind of read sometimes, not because I work with that kind of frameworks, but they will have a chapter on how to do like a reverb, or how to do like certain filter chains and things like that, which you can then kind of port to whatever you're using. And then there's where I usually find this. There's websites like which I find by Googling dumb things like that. DSP Related, where people put just the source code for very basic DSP operations like filters and in this case the zero crossing counter, which is useful for, I suppose, useful for things like frequency detection, and just show you how to do it. If you're coding in a low-level way, you want to not try to figure it out. Just kind of show you, and then co-pilots. I mean, you write a function called the zero crossing counter, and it'll kind of just give you that now. Like I use cursor now, and that kind of just has the lambda, not lambda, the Claude model in it, which does a lot of the work for me now with audio. I just need to kind of prompt it and hope. Sometimes filters can be risky because when you get one number wrong, it'll just kind of blow up. And then you will learn quite quickly how it's wrong.
Yeah. So the sine wave was a good base for the baseline and the drum and so on. But what if we wanted to have a noise channel for like percussion, like hi-hats and snares?
Yeah.
Those are usually constructed with
Yeah. Yeah, for that, just be rand. So white noise is essentially a random number between 0 and -1 and 1. So you can get rand from the C standard library, multiply that by 2, subtract 1, and you have a white noise oscillator, let's say. Most likely you will probably want to do, because that rand in standard library is a bit slow though, you want like a fast rand which isn't cryptographically secure or anything, because you don't need to be that. By making like a little twister algorithm or something that does weird numerical stuff to get you a quick rand function. So math.random is basically what we need for that. And if you need other types of noise than white noise, you can just filter that to get like pink noise or something else. Yeah, this is pretty good. Other questions, comments? I guess we're done. Thanks again.